Hi everyone, thank you for joining my presentation on accelerated discovery of stable and active materials for oxygen electrocatalysis. My name is Kasun, and I'm currently doing my postdoctoral research with Professor Jens Noskov at the Catalysis Theory Center in Technical University of Denmark. This work I'm presenting today is done in collaboration with wonderful experimental groups, Professor Hamio's group at Stanford University and Professor Kokendorf's group at Technical University of Denmark. In this presentation, I will discuss the importance of developing novel electrocatalysts for oxygen evolution reaction, then the theoretical framework developed to screen stable and active oxygen electrocatalysts. Finally, I will discuss further catalyst design strategies to improve OER activity. Some of the results I'm presenting today are just published in this ACS Energy Letters manuscript. And if you would like to connect with me, you can see my contact details here on the right. So we all are aware that achieving a sustainable energy future is critical to reducing our dependence on conventional energy sources based on fossil fuels, impeding climate change, and ultimately overcoming the ever-increasing energy demands. One aspect of this grand challenge involves developing sustainable energy storage and conversion technologies, as renewable energy sources like solar, wind, and hydro are intermittent. So electrochemistry plays an essential role to overcome this challenge as it allows transformation between electrical and chemical energy and vice versa. So this enables the storage of renewable energy in the form of chemical bonds. As the most efficient and the cleanest energy carrier, key solution involves storing the electricity produced by renewable energy sources as hydrogen by utilizing devices like water electrolysis, and electrical energy can be regenerated by fuel cells. Moreover, energy efficient upgrading of low-value chemicals to value-added chemicals is also possible based on cathodic electrocatalytic reactions such as nitrogen reduction to ammonia, CO2 reduction to long-chain hydrocarbons or alcohols. So water electrolysis consists of two half-cell reactions, the reduction at the cathode to produce hydrogen by the hydrogen evolution reaction, and the oxidation at the anode to produce oxygen by the oxygen evolution reaction. Similarly, fuel cells consist two half-cell reactions, oxygen reduction reaction and hydrogen evolution reaction. In this work, we are particularly interested in polymer electrolyte membrane or PEM devices over alkaline anion exchange membrane devices since they have the advantage of operation at high current densities and having higher stability towards load cycling and shutdowns. However, the main drawback of using PEM membrane is that most of the materials are not stable under harsh acidic conditions. So to date, the best known catalysts for OER in acidic solution are iridium oxide and ruthenium oxide and platinum for ORR. However, these catalysts have overpotentials of close to 0.4 volt. And most importantly, the high cost and the scarcity of these precious metals and the oxides hinders their commercial viability. Therefore, it is very crucial to discover and design the next generation of OER and ORR electrocatalysts that are stable in harsh acidic conditions, active, selective, and affordable. So in principle, there are two design strategies to improve the performance of a catalyst. One strategy is to engineer catalysts and support frameworks to increase surface area and exposed active sites, leading to an increase in geometric current density without a significant increase in cost, provided that we use cheap materials. Alternatively, on the right-hand side, new active sites can be designed that possess intrinsically high activity. So these strategies are, of course, not mutually exclusive, and a combination of both is ideal for practical applications. However, it is likely that further improvement beyond the current state of the art relies primarily on the later. So in this presentation, I will talk about how we identify a stable oxygen electrocatalyst, the high throughput computational screening framework to discover active OER catalysts, remaining challenges and strategies to improve OER activity. So most of the material screening studies for oxygen electrocatalysts to date are focused on the activity. However, to achieve a major breakthrough in discovering a promising OER material for PEM water electrolysis, an essential criteria is its aqueous stability under harsh oxidizing and acidic conditions. So aqueous stability of a material can be determined by computing the material's Gibbs free energy with respect to stable domains in the Pourbaix diagram as a function of pH and potential, as you can see here. So for example, titanium dioxide is stable over pH 0 to 14 and under typical ORR and OER potential ranges. So on the other hand, EHAL is the energy of decomposition of material into the set of most stable materials at a particular chemical potential composition. And this thermodynamic phase stability can be used as a metric to estimate the synthesizability of the candidate material. So higher the EHAL material or positive is more unstable and synthesis will be challenging. So in the first step, we narrow down the oxides from the materials project database, given that oxides are the most likely stable candidates under oxidizing conditions. Then to determine the stable materials, we use an EHAL criteria of 50 milli-electron volt per atom, which resulted in 23,605 stable oxides out of close to 50,000. Next, to identify acid stable materials, we evaluated the aqueous stability of oxides at pH 0 and under typical potential ranges of OER 1.2 to 2 volt versus SHE. We used the delta GPBX criteria of 0.5 electron volt per atom. Well, ideally, a criterion of less than 0 is preferred, but in a benchmark study of DFT predicted aqueous stability in experiments, it was shown that materials with predicted aqueous decomposition energies of up to 0.5 electron volt per atom could potentially be stable against corrosion in experiments. This is mainly due to the large solid-solid structural reorganization barriers originating from solid-only decomposition products. It is important to note that aqueous stability only indicates the bulk stability of a material and not the surface stability. Finally, it is somewhat depressing that by starting from close to 50,000 oxides, we only have 68 acid-stable oxides. Based on the composition of the 68 materials, we construct an acid-stable periodic table. From this periodic table, we clearly observe that antimony, titanium, tin, germanium, molybdenum, and tungsten-based oxides prefer being stable in strong acids. So most of the acid-stable oxide materials are ternary oxides, and the rest are quaternary oxides. A closer look at the space group of the material reveals tetragonal, orthorhombic, trigonal, monoclinic materials with various space groups, as you can see. Moreover, materials with a wide range of atoms in the bulk unit cells are observed. This variation of space groups and the number of atoms in the bulk structure of the acid-stable bulk materials indicates the structural complexity and the diversity of the surface models and their active sites. Moreover, for a given material, there are multiple exposed facets with different oxygen terminations, and these facets have multiple unique absorption sites according to the coordination of the absorption site. So most of the studies in the past address this complexity by focusing on a specific crystal system and/or a specific facet usually being the most dominant based on X-ray diffraction or XRD pattern. However, it is important to note that less stable surfaces could significantly contribute to the activity compared to the most dominant surface. So in this work, we overcame the aforementioned challenges for the high throughput catalyst screening by developing a workflow that systematically investigates the OER activity of acid-stable oxides. In the first step, we optimized the bulk structure and then generated the surface models that fulfill stoichiometry from their respective optimized bulk structure. So surface generation was only considered up to a maximum Mill index of 1. And for a given facet, there are multiple surfaces with different oxygen atom terminations. So to determine the most stable surface for a given material, we considered all of these surfaces and calculate their corresponding surface energies. and we use the one with the lower surface energy for a given facet. Then the coverage of reaction intermediates may significantly impact the local environment of the active site, resulting in changes in the absorption strength of the intermediates. So to determine the most stable surface coverage, we construct surface Puppet diagrams at three extreme coverages: pristine surface, OH covered surface, and O covered surface. And then we construct surface Puppet diagram, and we use the surface structure corresponding to the most stable coverage at 1.6 volt versus RHE for further activity calculations. Then we determine the theoretical thermodynamic OER overpotential, which is a measure of the activity of a catalyst. Now let's look at the scaling relationships. As shown in reaction 1 to 4, the associative OER reaction mechanism involves OOH, OH, and O as reaction intermediates. And it is well established that OER reaction intermediates follow linear scaling relations, since all the intermediates adsorb to the surface active site through an oxygen atom. At the first glance, a wide range of delta G OH values are observed. You can see it's ranging from range of 4 electron volt. And this highlights the diversity in activity of the acid stable oxides. As expected, some elements bind oxygen intermediates weakly, and we see this universal scaling for OOH versus OH. However, the OH versus O scaling is rather scattered. In this 2D OER volcano plot, we use delta GO minus delta GOH and delta GOH as a descriptor to plot the OER over potentials. Based on the current understanding, the optimal OER catalyst site has a delta GO minus delta GOH descriptor value in the range of 1.5 to 1.7 EV, based on the conventional mechanism and scaling relations. In the color scheme, red means it's a good catalyst with low OER over potential, and blue means it's a lousy catalyst. We notice that there are a few good catalysts, but most of them are pretty lousy. Cobalt antimonate, you can see here, iron antimonate, iron silver molybdenum oxide, molybdenum tungsten oxide, nickel antimonate, and titanium tungsten oxide. So these catalysts are affordable and consist of earth-abundant materials. So one-dimensional OER activity volcano that includes thermodynamic overpotential and delta GO minus delta GOH descriptor for the most promising acid stable catalysts are shown here. And we can see that the potential determining step for most of the inactive surfaces is OH oxidation to O, which is on the right side of the volcano. This indicates that O adsorbs weakly on these surfaces, and by increasing the O adsorption, we could reduce the calculated theoretical overpotential. Whereas on the right-hand side of the volcano, the oxygen adsorbs strongly, and therefore the potential is limited by the formation of OOH. We know from our previous slides that we have this universal scaling of delta G OOH equal to delta GOH plus 3.2. So for materials on the strong binding side, which is the left side of the volcano, so this scaling relationship defines the upper limit for how efficient an OER catalyst can be, since the ideal scaling would be delta GOOH equals to delta GOH plus 2.46. So to circumvent this scaling, an additional dimension of that site needs to be involved, which selectively stabilizes OOH intermediate compared to OH. In summary, I showed the high-throughput computational screening framework we developed to screen activity of diverse and complex acid-stable oxides for OER, which can be used to discover other functional materials as well. Then we identified a few acid-stable and active oxygen electrocatalysts for experimental validation. And in fact, these experiments are currently ongoing. And finally, we discussed strategies to improve OER activity and remaining challenges. With that, I would like to thank the amazing team at Cat Theory, and especially Professor Jens Noskow, also our experimental collaborators both at Stanford and DTU. This work was supported by Toyota Research Institute through the Accelerated Materials Design and Discovery Program. Finally, I gave a TED talk titled Hacking the Carbon Cycle Using Computers, and I invite you to watch it during your free time. Thank you and have a great day.